So for starters, we can define an exponential function as f of x is equal to a times b to the x, where a is a non-zero real number and b is any positive real number. The reason we don't want a to be 0 is, yeah, I suppose technically that is an exponential function, but f of x is just equal to 0 as a flat line, so you could kind of put 0 in a lot of classifications, and it's not particularly interesting for an exponential, so we just kind of avoid that. And the reason b can't be negative is then we might run into issues of what happens if we're doing a square root or a fourth root. So to avoid that whole headache, we say b is going to be positive. And this is kind of what the standard exponential graph looks like. Exponential functions are usually meant to model things that grow slowly for a little bit and then very quickly. And so that's exactly what's happening in this graph. Is we kind of start from our horizontal asymptote of y is equal to 0, and then gradually increase until we hit that y-intercept, and then we increase very quickly. And that's what a graph looks like if b is greater than 1. Now, if b is less than 1, and it still has to be greater than 0. So if b is a fraction, 0.5, 0.25, 1/8, something like that, it's the exact same graph, just kind of going the opposite direction. Those tend to be kind of things that decay. We talk about half-life of compounds and stuff like that when we're thinking of b being less than 1. Some additional facts about these graphs. The domain of any exponential is negative infinity to infinity. The range, and this is before any transformation, so again, this is kind of the base case parent function, if you will. If a is greater than 0, it's 0 to infinity, which is what's happening in both of these graphs. If a is less than 0, it's one of these graphs being flipped, so it's negative infinity up to 0. The y-intercept is 0, a, and notice how this is regardless of what b is, which makes sense. B to the 0, well, in fact, anything to the 0 is just 1. So if we plug in 0 into an exponential function, we'll be left with just a. And I've probably already said it twice. This is assuming we haven't done any transformation, so that can move up, down, left, right. But if we have no transformations, you already know your y-intercept is 0, whatever is in front of your exponential function. And then I talked about how the horizontal asymptote is y is equal to 0. And yes, in this case, we're actually not going to ever cross it, but that's not what it's used for. It's used for, again, kind of where does your graph start or where does your graph end. Now, evaluating an exponential. You don't really have to know a whole lot from the section to answer this first question. When you're evaluating anything, you say, okay, what function am I talking about? I'm talking about my f of x function. And I'm going to put in 5 for whatever my input is. So in this case, it's x. So to evaluate this, I just plug in 5 for the x in the power. And then 5 minus 3 is 2. 2 squared is 4. So then, skip a line. 3 times 4 gets you 12. That's more used for if you're going to check something, or if you want to go through and build your graph by painstakingly picking points. It's probably the least difficult, but also maybe the least interesting thing in this section, so that's kind of why I didn't linger on it very long. But one cool thing about exponentials is it is a very applied concept. You do see it a lot more than, say, graphing a rational function that we've recently seen. So in this case, we have a wolf population. You're told that in 2011 there is 129 wolves. In 2013 there is 236 wolves. Develop a model for this scenario. Now, I should have written this in the question. It should tell you develop an exponential model. Yes, we're dealing with population, so exponential functions are the best way to model population, but I should have specified it because you could have just as easily shown a linear model for this situation. Wouldn't have been very good, but it would have worked. So kind of look for that in the question if you're ever concerned of, should I be using an exponential or linear? It should tell you in the question, or you can certainly, if it's for any of our take-home tests, if there's a clarifying question, feel free to email me, and that's definitely a question I would say, yeah, do an exponential. I won't tell you how to do the exponential, but I will tell you to build an exponential model. Okay, so in order to build a model, I need to have some points to build around. Doesn't really look like I have points. It looks like I have a bunch of dates in this question, but hidden in those dates are actual points. So my model starts in 2011. So if I'm going to have a point, my first value is going to be time, and the second value is going to be the number of wolves. So in 2011, I had 129 wolves. So when I started year 0, I had 129. And then I look at 2013, well, that's 2 years past my start date, and I had 236 wolves. So my second point is 2, 236. Again, I'm not using 2013. I'm using the fact that since 2011 is my start date, 2013 is 2 days after it, that's my second point. You could do it the other way. Again, the model's not going to be as good, but you could have done your first point as 2011, 129, the math would be also a lot harder to deal with. Okay, well, I know an exponential model is f of x is equal to a times b to the x. That's the formal definition of before. And now we kind of have to find our a and our b. And it seems like it's a little bit more difficult, possibly just because we saw the definition. But this problem we've actually seen before just with a line, y is equal to mx plus b. If it wasn't in this course, it was probably a course before this for you guys. And we solve that equation by saying, okay, if I want to solve my m, or more specifically, if I want to solve my b, I plug in a point and solve for that value. So in this case, I'm going to do just that, but I'm going to use take advantage of a quality of exponentials that we saw in the last slide, of that any y-intercept is going to be 0, a. Well, I have my y-intercept here, it's 0, 129, so my first step is just to replace a with 129. And now my second step is kind of what I was getting into. Now I'm going to take my second point, I'm going to plug it into this function, I'm going to solve for b. So my f of x will become 236, my x will become 2, and then you just have to go about solving for b. Divide both sides by 129. I don't know why I wrote that twice. Square root both sides. And so b is approximately 1.353. Now my model is y is equal to, or f of x. F of x is equal to 129 times this b that I found, 1.353 to the x power. And that's usually what a question like this ends, is it asks you to build your model, call it a day. Well, usually kind of the natural next step in a question like this would be like, okay, great, you built your model. Now tell me how many you would predict in the future. So we're going to do that. We have our model. I'm asked how many wolves will there be in 2018. Well, I know again my start date is 2011, so I'm going to use my model and plug in 7 for my x. 2018 is 7 years past 2011. And then I just go ahead and evaluate like I did on my last slide, and I would find that I get 1070.72 wolves. Yeah, you could argue you can't have 0.72 of a wolf, so you could say 1071, but I would also counter that this is a mathematical model, and sometimes it's a good idea to leave it unrounded and say, yes, I know that's not possible, but this is what my model is saying, so take with that what you will. Maybe round down, maybe round up, maybe don't round at all. Now, kind of to remove the fluff of the word problem and just get down to a straight up question. I have 2 points. I want to find my exponential model. Well, oddly enough, the word problem in this case was the nice case, because I had a starting point, which means I could use the exponential function to just go ahead and say, oh, I know what my a is, and then go about solving for b. In this case, I don't have my y-intercept. I don't have an x is equal to 0. So instead, I'm going to have to write down the exponential model twice, that f of x is equal to a times b to the x, except for since I'm writing it twice, I'm going to plug in both of my points. So if I plug in my first point, 1, 6, into that exponential function, my f of x becomes 6, my x becomes 1. So I have 6 equals a times b to the first. And then I do the exact same thing with 3, 54. My 54 will be my f of x, and my x power will be 3. And now in this case, order doesn't technically matter. I recommend always saying whatever the highest power is, you put that above the lowest power for this next step. Now, while I don't know my a, I have two separate equations, and when I have two separate equations, two variables, I try and shrink it down to one equation. So I'm going to do that by actually dividing the second question from the first question. So that's kind of where that setup becomes important, because if I divide this out, then 54 divided by 6 gets me 9. A's will drop out, which is really great because we only want to solve for one variable for now. And then I'm left with b to the third minus b to the first is b squared. You kind of subtract the two. We'll talk about that more later, but I feel like that's reasonable at this point to assume that if you have something to the third power and you're dividing it by that thing itself, well, that leaves you with two of them. And now I just square root both sides. B is equal to 3. And yes, b is equal to plus or minus 3 in general, but we're dealing with exponentials, which means we can't have negative b's. Well, now I still have to solve for a. I want to find my exponential model. I want to find some sort of f of x is equal to a times b to the x. Well, since I have my b, I can go back and pick either of my starting equations and solve for a. In this case, the second equation is much easier than the first. So I'm going to plug in b, or 3 for my b, and 6 is equal to a times b to the first. So I get 6 is equal to a times 3 to the first, which is just, 3 to the first is just 3. So 6 equals a times 3, divide both sides by 3, a is equal to 2. Now, what tends to happen with questions like this is people get to this point and they say, okay, I did a lot of work, I found my a, I found my b, great job me, and move on from the question. No, the question's asking you to write an exponential model, so at the end of the day, you need something like f of x is equal to something. So we're going to plug in our a for the exponential model, our b for the exponential model, and we'll be left with y is equal to 2 times 3 to the x. Or if you want to, f of x is equal to 2 times 3 to the x. If it seems like you're confused where this equation keeps coming from, I mentioned it, I'll go back to the slide right here. So if you're looking at the top middle of the slide, it's that exponential model, that's the standard. The f of x is equal to a times b to the x. So that entire slide we just went through all revolves around that equation. That's how I built it. That's where I plugged my points into, and that's where I eventually put my a and b to get the final result that we saw. Okay, so now that we know what exponentials are, we kind of like to start to find a pattern in things and say, okay, well, we've seen linear models before. We know what those look like. Now we've seen exponentials. We kind of know what they look like. They're new. And there's probably a million other types of models that can be seen throughout mathematics. But as far as what we're going to be concerned about the course, it's either going to be those two or we don't know what it is. So we would declare it kind of as a neither. So I've got 3 tables here, and kind of my goal is to say, okay, is there a pattern in the table? And then the second question would be, what type of pattern would that be? Is it linear, exponential, or neither? And then if we are able to find a pattern in the table that we can recognize, then we want to kind of go that additional step and find the equation for that table. So we've already done this with a linear table before. This showed up on the first test. And so if we look at this first table, it should look at least somewhat familiar. Kind of have everything lined up, and I look and say, okay, 2 to 5 increases by 3, 5 to 8 increases by 3, 8 to 11 increases by 3. I'm going up by 3 every time, and that's an indication that we're dealing with a linear model, and that change is going to be my slope. And then the other thing to look for is, well, if we're building a line and we're using slope-intercept form, I need my slope and my intercept. So we said the slope is 3. My intercept is going to be 5. I know that because I can see on my table, okay, x is 0, and when x is 0, g of x is equal to 5, so that must be my y-intercept. So identify that it's linear, my y-intercept is 5, my m is 3, and so my equation is going to be y is equal to 3x plus 5. Now for the next table, try to look for a pattern. Let's see, okay, we're going up by, well, we're multiplying everything by 4. So 1/4 times 4 is 1, 1 times 4 is 4, 4 times 4 is 16, and then the last one's kind of hard to see, but 4 times 16 is 64. So that's what an exponential model looks like. Instead of adding something to each term, you are multiplying or potentially dividing something from every term. And so what we're doing is we need to, for an exponential model, we have that it's going to be y is equal to a times b to the x. So we have to identify what the a is and what the b is. And so the a in the exponential model is your y-intercept again. So in this case on the table, nicely enough, we have that it's 1. When x is equal to 0, h of x is equal to 1. And then your b in the y is equal to a times b to the x is just what you're increasing by each time or dividing by each time. So we're multiplying each term by 4 when we increase by 1. So I know my b is 4 in this case. So if I'm going to write an equation, it's going to be y is equal to 1 times 4 to the x. I don't write the 1 because it's kind of redundant. You could include it if you wanted to. I wouldn't penalize you on the exam, but you don't necessarily have to write it. I really want you to be able to identify them and kind of put them into one equation. Okay, so now this last table, if we look at it, there's clearly a pattern. We have the first y is equal to -1, the second one's 1, the third one's -1, the fourth one is 1. And this one actually isn't that hard to make an equation for, but it's not exponential and it's not linear. And so for the purposes of this question, we just say neither and we stop. Okay, in this slide, we're going to go over some exponential rules. We'll use these when we're solving equations, and we'll see them again when we're getting into logarithms. We kind of vaguely reference it in that section. So this might be a good thing to take a picture of or jot down in your notes for reference. That being said, there's a good chance you've seen the majority of these before. So if you're preparing for the next test and writing a note card, I might not take up a lot of space on that, writing these down. So the first one is, or kind of the first two that are used most often, is that if I have an exponential and I'm multiplying it by another exponential, I'm allowed to add those powers. But I'm only allowed to add those powers if they have the same base. So the same thing applies with division. If I'm dividing two exponentials, I can subtract their powers. So for example, if I have 2 to the third over 2 to the first, that becomes 2 squared, 3 minus 1. But if I had something like 2 to the third over 4 to the seventh or something like that, I can't use that rule to make it into a single exponential. So some of the other less famous ones are that if I'm taking an exponential and I'm putting that in parentheses and taking it to a power, that's the same thing as multiplying those powers. If I have two numbers that I'm multiplying and those things are being taken to a power outside of their parentheses, I can just distribute that power to both. So a times b to the s is the same thing as a to the s times b to the s. 1 to any power is 1, which makes sense. 1 squared is 1 times 1 is 1. 1 to the 100th would be 1. If I have a negative exponent, that means what I'm going to do is I'm going to move it to the bottom of a fraction and then it will become positive. So if I have like 2 to the negative third, that's the same thing as 1 over 2 to the third, and then it would kind of resolve that if I had to. And I'm able to, since 1 over a to the s is the same thing as 1 to the s, I can kind of bring that power outside and just make it 1 over a to the s. That's kind of the least important one. So if you didn't track that part, that's perfectly fine. And then the last rule in this one is pretty important and kind of one of those unfortunate things that you kind of have to just take my word for it. That being said, there is a proof behind it as to where it comes from, but it's not really worth knowing the entire steps to just say simply, if I take anything to the 0 power, I will get 1. So if I have 1 to the 0 power, I get 1, which follows kind of from a previous rule. If I take 2 to the 0 power, I will get 1. If I take 1 million to the 0 power, I will get 1. We're going to kind of use a neat little trick to solve them. And this neat little trick is that if we have the same base of an exponential, then we can set the powers equal to each other and then potentially solve from there. So for example, I have 5 to the 2x is equal to 5 to the 3x plus 2. All those bases are exactly the same. I can set the powers equal to each other, and then I can just solve from there. I would subtract both sides by 2x. I would subtract oh no, I subtracted 3x from both sides. Then I would divide by -1. I would get x is equal to -2. And we can go ahead and check this answer. It's not that hard with an exponential. I think we'd have to have a calculator because we'd have to evaluate 5 to the 4th at some point. But it's worth checking, and then eventually when we get into logarithms, you will have to check it. Otherwise, you could have extraneous solutions. Now, sometimes it looks like we can't really solve it with this trick, which is true for now. I don't have the bases equal to each other. One of my bases is 25, the other one is 5. So I can't just set the powers equal to each other. But those look like they're kind of related. Like when I see the number 25, I think, okay, that there's a lot of things I can do with 25 when I start thinking about 5. And so if you kind of see maybe this vague relationship, then you can start talking about, okay, is there something I can take the power of 5 to in order to get 25? Or maybe if I could reduce it to a lower power and then get it up to 25 like that. So in this case, long-winded way of saying, 5 squared is 25. And so what I can do is I'm going to leave the 5 alone on the left side, but the right side I'm going to say, okay, I don't actually want to deal with 25. I'm going to say 25 is equal to 5 squared. So I can rewrite the right side as 5 squared, and then it's just times 3x plus 2. So now I actually have like bases. I just have to distribute the 2 to the power. So 2 times 3x is 6x, 2 times 2 is 4. And now I just do exactly what I did in example 1. I set both things equal to each other. I subtract 6x from both sides. I divide, I get x is equal to -1. And then again, if I want to check my answer, good idea, not super difficult. I would just plug -1 into my original equation, and both sides of the equation should be equal to each other. Now, this is where we're going to start to bring in logs into the equation, because honestly, probably the main reason logs were invented were to kind of resolve this scenario of saying, okay, I want to solve this equation. I obviously can't divide both sides by something or subtract things from both sides in order to get x by itself. So in order to undo my exponential, I'm going to use a logarithm. So I'm going to translate 5 to the x is equal to -100 by moving that base over to the other side and saying x is equal to log base 5 of -100. Or I could use the fact that when I'm dealing with an exponential, I can't have a negative result, because an exponential's range is 0 to infinity. So that would be a graph kind of that swoop that goes up to the right side. So I would get no solution. If we wanted to kind of continue with my line of thinking with my logarithm though, very similar logic. I would translate it. I would get x is equal to log base 5 of -100. I can't have a negative input with my log, so I would also get no solution. So as a bit of a review, kind of basic properties of, in this case, we're going to be less general. We're going to say straight, our parent function is y is equal to 2 to the x. Key points are 0, 1. That's going to be my y-intercept before any transformations. And then if I plug in 1 into my equation, I'll get 2. And if I plug in 2, I will get 4. And so those are going to be our 3 key points when we're going through this transformations. The other kind of parent function is if b is between 0 and 1, and we typically talk about that with 1/2. And the key points for that, I don't think we'll kind of see an example in this section, but the key points for that are going to would be, again, 0, 1, and then 1 and 1/2, and 2 and 1/4. The reason that we don't really talk about it much in this section is because it's fractions, and fractions can cause a bit of a headache, but it's perfectly fine. The concepts apply exactly the same. You just have to be careful when you're adding and subtracting. So we talked about in the very general case, y is equal to a times b to the x, and your horizontal asymptote is y is equal to 0. That is true from both of these parent functions as well. The same horizontal asymptote, same domain, -infinity to infinity, and the same range that we saw in the last lecture, 0 to infinity. So we got to keep all of that in mind when we're kind of maybe ask questions after our transformations of what's our new domain or what's our range. Or specifically, we like to, in this class, talk about what happened to the horizontal asymptote. So keep those 3 things in mind. X-intercept is none, because we have that horizontal asymptote if y is equal to 0. Y-intercept is 0, comma a, or when we were talking about y is equal to 2 to the x, 0, comma 1. And we don't really talk about that this much in this section. That's why I'm actually not going to fix the error on this one. The graph is going to be increasing if b is greater than 1, and it's going to be decreasing if b is between 0 and 1. So it's that, is it a exponential growth? B is greater than 1. Yes, increasing. Is it exponential decay? Between 0 and 1, then it's decreasing like the graph on the right. So now I have a function. Y is equal to 3 times 2 to the x minus 2. So I can kind of recognize that my parent function is going to be 2 to the x, and I will write down my transformations after I put down my key points. Yeah. So I will write down my transformations, but originally my key point for y equals 2 to the x is 0, 1, 1, 2, and 2, 4. So I'm going to start with those key points, and then just like we did in the transformation section, we're going to describe our transformations. And so the first transformation is I've stretched vertically by 3, and my second transformation is I shift down by 2. Now you might be remembering when we talked about transformations, I'm not super concerned about the terms stretch or shrink because, in my opinion, they are fairly arbitrary. But it is worth mentioning the transformation just when you go through the process, whatever helps you remember what you're doing. So I would, if I was not making a formal slide of this, I would not say it's vertical stretched by 3. I would say multiply y by 3 because that's exactly what you're going to do. But formally, you are stretching your graph vertically by 3. So now we apply these transformations to our 3 key points. To vertically stretch by 3, well, as I just said, we multiply each y value by 3. So my first point will become 0, 3. My second point will become 1, 6. And my third point will become 2, 12. 2, 12. Now I have to apply my next transformation. I'm shifting down by 2, and down is also going to be applied to the y values. So I'm going to subtract 2 from each of my y values. So my first point now becomes 0, 1, my second point becomes 1, 4, and my third point becomes 2, 10. And remember that it's that idea that we talked about in the transformation section of inside and outside. So in this case, the inside would be my power, and so if I'm doing anything to the inside of my function, I would be applying that to my x values. And then outside of my function, outside of my 2 to the x, is where I'm going to apply things to the y value. So in this case, it just so happens that both of my transformations were outside of my parent function, and so that's why I'm only applying them to the y, but it's not always going to be the case, so be aware of that. And from there, I'm going to plot my points. So one of my key points is now 0, 1, one of it is 1, 4, and the other one is 2, 10. And I know my graph shifted down by 2, so I will have a horizontal intercept at y is equal to 2. And finally, I know the shape of my graph. It's 2 to the x, so it's that exponential growth, almost that like swoosh to the positive section. So yeah, it might be tricky to think about what an exponential function looks like, but really we're playing that game that we've played several times in this course of connecting the dots. I'm going to plot my points. I'm going to say my horizontal intercept is y is equal to 2, and as long as you draw a graph that goes through those points and doesn't cross your horizontal asymptote, you'll get full points for the question. Oh, there it is. Kind of hard to see because it got cut off. But it's saying right there at the bottom of the slide, the y horizontal asymptote is y is equal to -2. Now, I could be given a graph, or I could be just have a graph described to me, and I might have to go back and write the actual equation. So in this case, I'm not actually going to do the graph. Instead, I'm going to describe what's happening in the graph. But really, that's only one step removed if you had a graph in front of you. So in this case, we are told we have an equation of e to the x. Well, I don't think we've seen e to the x before. It doesn't matter. It's an exponential. So we're going to just say, okay, now my parent function is e to the x as opposed to 2 to the x. So it's fine. If you are curious, e is a very important number. We see it a lot when we're modeling population. So we give it its own special fancy variable, and I believe it's 2.7 something. I could look that up. So it is an actual number. It's not a variable. It's kind of like pi. We give pi its own value. And so that's what's happening. It is an exponential. It is a value, but instead of writing down a weird decimal, we just call it e. Okay, all of that aside, we want to apply transformations to this graph that is e to the x. I know my horizontal asymptote is now as y is equal to 3, and I also know that it is going to be reflected over the x-axis. Okay, well, I know that if it is a horizontal asymptote of y is equal to 3, well, my graph better be shifted up 3 units. So I'm going to add 3 to my e to the x, so I know at least I'll have e to the x plus 3. And then since it's being reflected over the x-axis, a vertical flip, that means I'm going to multiply e to the x by -1. So if I just connect those two dots, I have y is equal to negative e to the x plus 3.